In this video we're going to tackle section 2.4, continuity and one-sided limits. Continuity is an underlying principle of calculus. Without a continuous function, we can't do all these fancy calculus operations to it. And we have been talking about limits since the start of chapter 2, and I've sort of brought up the terminology and hinted at this in an earlier section. But we're going to look at limits now just from one side. Remember, limits, if we got like a hole in the graph, we're approaching that hole from both sides. Now we're just going to look at what happens as we approach from this left side, or from numbers less than, whatever C value we're interested in. Or we might look at the right-handed limit as we approach from a number greater than C on the x-axis. And in this section we're going to determine continuity at a point and continuity over an open interval. And then we're going to look at these one-sided limits and continuity on a closed interval. On our x-axis, maybe we're not worried about what's going on across the whole function. We're only worried about maybe from like this x value, we'll call it A, to this other x value, we'll call it B. We're going to have this closed interval, and we're just worried about what's going on over that closed interval. We'll use properties of continuity. Those are very similar to the property of limits in general. And we will understand this intermediate value theorem, the IVT. Alrighty, let's get started. Continuity at a point and on an open interval. In mathematics, the term continuous has much the same meaning as it has in everyday usage. Informally, to say that a function f is continuous at a point C means that there's no interruption in the graph of the function f at that point. That is, the graph is unbroken at point C, and there are no holes, or no jumps, or no gaps. The figure below identifies three values of x at which the graph of f is not continuous. All other points on our interval from A to B, the graph of f is uninterrupted and continuous. So here we're looking at an open interval. If we look at the left side of the graph, we have this open circle. On the right hand side here we also have an open circle. And here we see in the center of it we have a hole in the graph above point C. F of C is not defined. On this second graph here, we have, again, our endpoints. It's an open interval, A and B. And here we have a big gap in the graph. As we're going along, we sort of jump from this defined point here down to an undefined point, and the graph picks up again. We have that big gap in the graph. There, our limit does not exist. The limit as we approach C from the left, we're up at this number. As we approach C from the right, we're down here at this number. So we're approaching two different numbers, and that limit does not exist. And here in the last case, the function is defined. F of C does exist. It's a point down here. This limit does exist. As we approach from the left, we're approaching this hole. As we approach from the right, we're approaching that same hole in the graph. So the limit exists and the function is defined, but they're not equal. This hole in the function, we sort of took that point out and moved it down here. So there are the three conditions for which the graph of our function is not continuous. We got a hole in it, we have a gap in it, and we could have a hole, but we're also defined. So here again, let me just say we got a hole, and our function is undefined. Here we just have a gap or a break in the graph, and here we have a hole, but we are defined. So those are three times when a function is not continuous at a point C. Remember, in a nutshell, continuity is, can you put your pencil on your paper and draw the graph without lifting it off the paper? If we lift our pencil off the paper, we can create a hole like this. Or if we lift our pencil off the paper and put it down over here, we create this big gap in between these points. So this leads to our formal definition of continuity. Let's just plow through it and then we'll discuss it. Continuity at a point. A function f is continuous at point C if the following three conditions are met. F of C is defined. The limit as we approach C exists. And third, brings them together and says, these are also equal. Now, when I think about this, I think the only important one is number 3. Because if the limit exists and the function is defined, and they are equal, that implies the first two. I mean, we couldn't have number 3 if number 1 didn't already happen, our function is defined. And we wouldn't have number 3 if the limit actually exists. In number 3, again, just ties them together and says that they are in fact equal. When it comes to the AP test, there could be a multiple choice question on this, or it might even be part of a free response. This is something to commit to memory. The 3-part definition of continuity. The function is defined, the limit exists, and that they are both equal. And here we have continuity on an open interval. A function is continuous on an open interval from a to b, and we use parentheses to say that the endpoints are not defined, if it is continuous at each point in the interval. A function that is continuous on the entire real number line from negative infinity to infinity, we call that everywhere continuous. Okay, consider an open interval I that contains a real number c. If the function f is defined on that interval, except maybe at that point c, and f is not continuous, then f is said to have a discontinuity at c. Discontinuities fall into 2 categories: removable discontinuities and non-removable. A discontinuity at that point c is called removable if it can be made continuous by appropriately defining or redefining the function. And that's removing the discontinuity. We did that when we analytically looked at limits and we factored and reduced common terms, or when we rationalized is another way to remove a discontinuity. So let's look at the first one here. This would be a possible removable discontinuity. We just have that little tiny hole, and it might be possible to factor or rationalize and pave over that hole. So that one would be removable. Here we have a gap, a jump, or maybe even an asymptote. That is going to be non-removable. There's nothing we can do to that function to close that gap. In our third case here, remember we have a hole in the function, but we are maybe defined down here. That would also be a removable discontinuity. We have to have the limit existing as we approach from the left and the right to possibly remove that discontinuity. Also here, we need the limit from the left to equal the limit from the right. That limit has to exist to possibly remove that discontinuity. Here, as we approach from the left, we're up at this number. As we approach from the right, we're down here at this open spot. So that limit does not exist, and there's no way we can close that gap. So here in example 1, let's check out some functions and discuss the continuity of each function. Let's see, here is the basic rational function, 1 divided by x. So what number is going to mess us up here? Well, if we plug in a 0, if we divide by 0, the world's going to blow up, of course. So we have a discontinuity at that point. If we remember the basic shape of the graph of that rational function, it looks like this. We can't plug in 0 as we approach 0. As we get infinitely close to 0, we're dividing an infinitely small number into 1, which gives us an infinitely large number. So we're heading up toward infinity, making the y-axis our vertical asymptote. As we approach from the left side, negative numbers, very, very close to 0. We divide that positive 1 divided by an infinitely small negative number. We get a negative infinitely large number. So we're going down toward negative infinity. So that is a discontinuity. We are defined everywhere except at 0, and that's going to be non-removable. So A is non-removable. Then I'll just put in there asymptote. SM. We have a vertical asymptote there. It's going to be a non-removable discontinuity. Letter B, we've seen a few functions like this before as we discussed limits and how to find them. It looks like we're going to be able to factor this. Our function is a squared divided by a first power, which gives us x to the first, so that is going to be a straight line. A straight line with a removable discontinuity at x is 1. So there's our straight line. Above x is 1. We do have a hole in the graph, but that is going to be removable. And that's an easy fix if we factor the numerator to an x minus 1, x plus 1, and we divide by x minus 1. That common term will cancel. So the limit, we can just plug in our 1 and get 1 plus 1 is 2. So that is removable. We can factor to remove that discontinuity. Removable. and removable by factoring. All right, let's look at the next one. Here we have a piecewise function, and we've been dealing with these more in calculus than we saw in pre-calc, and we're worried about the continuity of this function. Now here it says for all numbers less than or equal to 0, we plug those numbers in for that x. For all numbers greater than 0, we're going to take that x and plug it in here. So where we're really worried about, well, let's discuss even the pieces first. X plus 1, that's just a straight line, that's continuous everywhere. The other piece of the function is x squared plus 1. That is also continuous everywhere, just a parabola opening up. So where we're really worried about is at this x value. At this point is where we jump from one piece to the other. So this is an easy check. I'm just going to plug this 0 in for this x, and I get 0 plus 1 is 1 for the top piece. And if I plug 0 into the bottom function, I get 0 squared plus 1 is also 1. Since those are equal, you know our function is uninterrupted. So that's going to be no gap in the graph, continuous everywhere. Continuous everywhere. Or you could write all real numbers. And let's check at the graph of this one. So to the left of 0, less than or equal to 0, we got a straight line, 1x plus 1. So there's our y-intercept at 1, and our slope is going uphill. But right when we get to 0, we stop graphing the line, and we start graphing the parabola. The parabola is x squared plus 1, so it also has a y-intercept at plus 1 on the y-axis, and then it turns into a parabola opening upward. So here I'll use red for the parabola. The black part is the line, and then we jump right onto the parabola. There is no gap there. If that happened to have been an x squared plus 2 function, then our parabola would start up here at 2 with an open circle and go up. Here we would have a discontinuity. And we would have seen it when we plugged 0 in. We would have had 0 squared plus 2 is 2. And then our first piece gave us a 1. Our second piece gave us a 2. Those are not equal, so that would be non-continuous at that point. But the one that the book did give us, that did check out. So we'd also write from there, that is all real numbers. All real numbers. And really, we just had to check at 0. We checked out this point, plugged it into both functions to make sure they were equal. So finally, discuss the continuity of y equals sine of x. Well, of course, that's just the sine wave. You know, we start at the origin, and we go out to infinity, just waving back and forth. Same thing as we had to negative infinity. So that's also going to be continuous everywhere. All real numbers. Everywhere continuous. All right, let's talk about these one-sided limits and having continuity on a closed interval. So to understand continuity on a closed interval, you need to look at a different type of limit called a one-sided limit. For example, the limit from the right, or the right-hand limit, means that x approaches c from values greater than c. And we denote this as, we put this little plus here. The limit as x approaches c from the plus side, or from the right-hand side, of our function f of x is equal to L. That's our limit from the right. Similarly, the limit from the left, or the left-hand limit, means that x approaches c from values less than c. And this is denoted with a little negative sign up there. The limit as x approaches c from the left side of our function is equal to L. And let's check that out as a graph. So here we have x approaches c from the right. You know, here's our c value. We're maybe assuming here it's the y-axis. We're approaching c from the right-hand side. So this would be the limit as x approaches c. And I think, you know, here we're approaching from the plus side on the x-axis. So we'll put the little plus sign there of f of x. And we can also approach from the left-hand side. So here we're using c is going to be greater than x. Our limit as x approaches c from the left side, or from the negative side of the x-axis, of our function f of x is equal to some limit L. And I did give a hint about that, I think, a couple sections ago when we were first talking about limit. I did make a reference to left and right-handed limits. So here, example 2, we'll check out one of these one-sided limits. Find the limit of f of x is, here's our function, the root of 4 minus x squared as x approaches negative 2 from the right. Now this is a pretty common function in calculus. F of x is equal to, you'll see a radical with a number minus x squared. So it's a good idea to commit this to memory that is half of a circle. Because if I have this written as y equals the root of 4 minus x squared, if I square both sides, I get y squared equals 4 minus x squared. And then I would add x squared to both sides. X squared plus y squared equals 4. And remember from pre-calculus, x squared plus y squared equals radius squared. That's the formula for a circle. For a full circle. Remember when we square root, though, there's a plus sign in front of this. We're only going to get the positive half of that circle that exists in the first and the second quadrants. You might see a similar function where there is a negative in front of that radical. That would just give us the under part of the circle, the half of the circle that exists in quadrants 3 and 4. So that's a common one that pops up. You might see it on the AP test or a test in this class. So a root of a number minus x squared is just half a circle. If you square root the number under the radical, that's your radius. So we know for this problem in example 2, if we take that 4 and square root it, we got a half circle radius 2. So here's our graph xy axis. We're going to go from 2 to negative 2 on the x-axis, and of course up to 2 on the y-axis. So there is our half of a circle. Again, if there was a negative here, we would only have the underside of that circle in the lower quadrants. So they're asking us to find the limit as we approach negative 2 from the right. So if graphically, we could just look here at the negative 2. You know, this is a limit we cannot approach from the left. You know, our function is not defined any number less than negative 2. So here we can only approach from the right. And on the x-axis, we're approaching negative 2 from numbers, you know, a little bit above negative 2, which means as we plug those x values in, we're sort of sliding down this half of the circle. What is our limit on the y-axis as we approach negative 2 from the right? Well, that height, when we get real close to there, our height on the y-axis is going to be 0. So as shown in the figure, you know, as we approach from the right, the limit as x approaches negative 2 from the plus side, or the right-hand side, of our function is equal to 0. And you know, you can do that kind of without the graph. We're approaching negative 2 from numbers a little bit above it. So I would just think in my head, negative 1.9 or negative 1.99. If I plug those x values in and I square them, I'm getting very, very close to a positive 4. But not quite a positive 4. So it's going to be 4 minus a number really, really close to 4, which as, you know, we get that number closer and closer to 2, we're going to approach a value of 0. 4 minus a number that's almost 4 is getting us closer and closer to 0. Alright, one-sided limits can also be used to investigate the behavior of step functions. Remember, we saw these in pre-calc, and I referred to them. You can also call them, you know, rounding down functions. One common type of step function is the greatest integer function. Yeah, that's the rounding down function. And we sort of have our x in these little double bars, almost like absolute value bars, but they're double, and we got a little hook at the top and bottom. So the step of x, or the greatest integer n, such that n is less than or equal to x. It's sort of like rounding down. So if we do the step of 2.5, we round it down to 2. Careful with negatives. The step of negative 2.5 is negative 3. And graphically, these were pretty interesting functions. So, you know, we're just going to have little horizontal bars. From 0 to 1, we round everything down to 0. From x values from 1 to 2, you know, all the fractions and decimals in between 1 and 2, we round them down to a height of 1 on the y-axis. All the numbers between 2 and 3 get rounded down to 2. And of course, we are defined on the left-hand side of that bar, and as we go across, right as we get to 2, there's a hole here, and we step up to the next segment of the graph. So example 3, the greatest integer function. Find the limit of the greatest integer function, f of x equals the step of x, as x approaches 0 from the left and the right. From the left and the right. So actually, let me slide the graph over here. So the limit as x approaches 0 from the left-hand side of our step of x, so we're approaching 0 from the left. Here's 0 on the x-axis. We're approaching that from the left-hand side, so we're at numbers less than 0, and it looks like we're approaching this number here on the y-axis of -1. Now let's look at the right-hand limit. The limit as x approaches 0 from the right side, or the plus side, of our step function of x is equal to, so here again we're approaching 0 on the x-axis. We're approaching along this segment of the graph, and that looks like we're approaching right at a height of the origin, 0. And this here is going to lead us into the formal definition, or Theorem 110, the existence of a limit. When the limit from the left is not equal to the limit from the right, the two-sided limit, or the overall limit, does not exist. The next theorem makes it more explicit. The proof of this theorem follows directly from the definition of a one-sided limit. So our Theorem 110 is, when does a limit exist? Let f be a function. Let c and l be real numbers. You know, c is just the x value we're approaching. L is some number on the y-axis that will be our limit. The limit of our function, f of x, as x approaches c is L if and only if the limit as x approaches c from the left is equal to that L, that limit, and the limit as we approach from the right-hand side is also equal to L. Remember, when we did this graphically, or when we first introduced limits, if I had a setup like this, here's my function, got a little hole in it. Here is our c value. So all we're saying here is, as we approach c from the left-hand side, we're sort of moving up the graph, and we're approaching on the y-axis this number L. As we approach c from the right-hand side, the right-hand limit, we're sort of sliding down this part of the graph toward that same hole at that same height. This is just saying the limit from the left has to be equal to the limit from the right. These two are both equal to L, so they are both equal to each other. The limit from the left and the limit from the right are the same. And that just means graphically that we're approaching that same hole in the graph, or that same point in the graph, at that height, L. And I made this up. This is not in your book, but I did just make this up to, graphically maybe reinforce it a little bit. Here we have our limit of our function, and we're worried about the number 5. On our x-axis here is a x value of 5. So let's look at the left-hand limit. The limit as x approaches 5 from the left, as we're approaching, 5 from the left here, we're moving up this graph, and we're approaching, it looks like a limit of, that hole is at a height of 2. Now the right-hand limit, the limit as x approaches 5 from the right, we're sort of, now we're on the x-axis above 5, so that means we're on this part of the function sliding down, and that looks like we're approaching this closed dot here, and that's at a height of 4. So the limit from the left is 2. The limit from the right is 4, but the overall limit, the limit as x approaches 5 of the function, dne, it does not exist. And remember, there were 3 reasons why a limit could not exist, and this reason is we're approaching 2 different numbers. Our left-hand and right-hand limits do not agree. We're approaching 2 different numbers, so the overall limit does not exist. The left-handed limit exists. The right-handed limit exists. They're not equal, so the overall limit, dne, does not exist.